Thank you, Elizabeth, for the introduction. Hello, good evening. I'm Nivedita Bhakhta. I'm a faculty member at IIT Kanpur in the Management Sciences department. Today, I'm going to talk about causal inference, walk you through what causal inference is, what are some of its building blocks, and then help you all to evaluate some of the research designs that are typically used in research all around us. Yep. Okay. So the agenda for the talk is such. We will start with a basic background of causal inference. Then we will try to see what cause and effect is, the definition of it in research. And then we'll see how we can make use of different kinds of experiments to draw causal claims. Then we will see what are some of the threats to validity of these causal claims. We will look at a couple of case studies, and then finally, we will have a discussion about how to evaluate research designs in causal inference. So why causal inference? We are all surrounded by causal claims, right? Whether you are a statistician or a student who is interested in knowing more about causal inference and causal inference-based models, or whether you're someone who doesn't want to do anything with data, mathematics, computation, nothing, and you don't even want to do research, but you're still surrounded by a lot of causal claims. So whether you are the producer of the research or the consumer of the research, causal claim is everywhere. So it is better that you acquaint yourself with some of the basic concepts of causal inference so that you are in a better position to judge and make your own decisions about what to do with these causal claims that are thrown at you, right? So this talk will try to equip you with some tools in your arsenal so that whenever you are bombarded by WhatsApp university messages, you are in a better position to make sense of those, right? Okay. So there are two major building blocks of causal inference. The first one is correlation, and the second one is causation. How many of you are familiar with the term correlation? I see some hands up. Okay. So let's quickly take a look at what correlation is. So correlation is a statistical measure that basically describes the extent of the relationship between two variables, right? It provides us with it describes the linear relationship between the two variables, and it basically tells us how the two variables behave. That is, when one variable increases, what happens to the other variable, right? There are three different types of correlation. We have positive correlation, we have negative correlation, and then we have the case where there is no correlation. In positive correlation, we see that if there are two variables, let's say one variable is the amount of time you have spent studying, and the other variable is your test score, right? We say there is a positive relationship when you see that, as the time spent studying increases, your test score increases. Right? Then there is a negative relationship or negative correlation. That's when, let's say, one variable is the amount of time you spend on social media, and the other one is your test score, right? Now, as the amount of time spent on social media increases, your test score decreases. That is negative correlation between the two variables. And then you have scenario where you are probably dealing with independent events or independent variables, and you don't see any correlation, right? Okay. The next thing, so now that we are familiar with the first block, let's look at the second block, which is the causation. Because causal inference is incomplete without talking about causation. As you can infer from the meaning of the English word causation, here causation refers to the phenomena in which when you change one variable, it directly affects or causes a change in another variable, right? So one of the examples we can think of is, let's say I have a headache, right? When I take, let's say I take a tablet, and then I see how my headache, whether it has improved or whether it has worsened, right? Now I can say that taking the tablet has caused a change in the levels of my headache or levels of my pain. Now this is a causal relationship, right? One variable is causing the change in another variable. The variable taking the drug or not is causing a change in the levels of my pain or levels of my headache. So here causation refers to the phenomena where the change in one variable affects the change in the other variable. So as you can see, correlation and causation are quite related in certain sense, right? Correlation tells you the extent of the relationship between two variables, and causation tells you how the change in one variable affects the change in the other. So now, that brings us to this question: does correlation imply causation? They seem quite related, right? So how many of you say that correlation implies causation? A few hands. Okay. How many of you think correlation does not imply causation? A few hands. Some of you have not made up your minds yet, which is not bad. So if you were among the people who said that correlation implied causation, I have a bad news to tell you that it does not, right? So correlation here, even though correlation and causation are related, correlation does not really imply causation. That is because we have something called spurious correlation. What exactly are these? Let's take an example of ice cream sales and shark attacks, right? Can you see what the graph is trying to tell you? So you're seeing that, it is, we are seeing a distribution of ice cream sales and shark attacks over the entire year. We see the peaks during the summer months, right? And both are behaving in similar way. So we can say that there is a positive correlation between shark attacks and ice cream sales. Can I say that eating ice creams causes shark attacks? No. Otherwise, you'll have to be really careful, right? Next time you're eating ice cream, you better beware and, look around you whether there are sharks. At the same time, I cannot say that if you are a victim of shark attacks, you suddenly start eating ice cream more. Right? That is also not something I can conclude from this. Okay. Similarly, let's look at another example. Here, on the x-axis, I have chocolate consumption. On the y-axis, I have Nobel laureates per 10 million population. On the x-axis, the chocolate consumption is in kilograms per year per capita. And you see Switzerland all the way up there, right? Very high chocolate consumption and very high number of Nobel laureates. So I think here I would tell the organizers that, instead of having all these workshop worksheets, homeworks, and quizzes, let's just prescribe chocolate for breakfast, lunch, and dinner, right? And here we are going to have all Nobel laureates. But sadly, no, that is not the case. We cannot draw, even though we can see the correlation is 0.79, which is quite high, right? We cannot really draw the conclusion that consuming more chocolate leads the particular country to have more Nobel laureates. Or in other words, eating more chocolate leads to a higher IQ, or however you want to conclude. Also, it's quite weird if you see that, these measurement, it is per kilogram, it's kilogram per year per capita. So on an average, people in Switzerland consume more than 11 kgs of chocolate, right? So the way the chocolate consumption is measured in itself is problematic. And also, Nobel laureates per 10 million population. Do you think that Switzerland, Sweden, Denmark, Norway, all these countries have a population of 10 million? Probably not, right? So one thing is that apart from the correlation, we also should be mindful of how our variables are being measured. But we are not going to go deeper into this particular aspect of measurement error in our variables, but we are going to stick with correlations. Okay. So spurious, yeah? Yes. Sure, but it is also an example of correlation, right? In some cases, you can have correlation can help you move towards causation, but that is not the general statement, right? In general, if you just have correlation, does not guarantee you that there is causation. There are ways, we are going to discuss the ways in which we can move from correlation towards causation. Okay, but what we saw in these two examples is nothing but spurious correlations. What it means is that two variables can seem to be correlated, or we can see that there is some positive or negative but strong relationship between two variables, but that might just be a mere coincidence, or it might be influenced by a third variable. Like in the shark attack and ice cream sales, maybe it has got something to do with summer months. When people are out, they're vacationing, they're going to the beaches, and also they're having ice creams, right? Similarly here, there can be so many other factors at play. We saw that, whenever the countries like Switzerland, Germany, Sweden, all these, they had high number of Nobel laureates as well as higher chocolate consumption. It could be due to so many underlying reasons such as higher GDP, better educational infrastructure, and so on. So we cannot just base causal claims when we are observing correlations just by itself. There needs to be something more. And we are going to see what that something more is. Okay. So we know what correlation is, we know what causation is, and we know what spurious correlations are. And now we know we cannot be fooled by correlations. So how do we move from correlation to causation? Because a question was asked that in the example of hours spent studying and test scores, there is correlation, yes, but then there is causation also, right? Now, if you have spent more time studying, you're probably going to do well in your test. So in order to move from correlation to causation and to establish causal effect, there are three properties that we would need to satisfy. The first is that the cause should be related to the effect. The second is that the cause should come before the effect. That is, there is a temporal precedence. The cause needs to happen before we can see an effect. The third is that there should be no plausible alternative explanations for the cause that we are observing. Or sorry, for the effect that we are observing other than the cause. So cause has to be the main driver or the only driver of the effect that we are seeing. Now there are some smiley faces attached to these three properties, right? That's because in the first one, the first property where the cause has to be related to the effect, that's a rather easy to satisfy property, right? We can look at the correlations, we can look at all sorts of relationships between the two variables and see whether they are related or not. That's easy. Then the second property is that we have to establish a temporal precedence of cause and effect. We have to show that the cause has happened before we saw the effect. Now, in most of the experiments that you will conduct, that is going to be the case because you will be in charge of monitoring the experiment. You will see how you are determining the treatment, how much treatment you are giving to whom, and so on. In that case, it's quite straightforward. You know that the cause has happened before effect. But in a lot of social science research that we see around us, this becomes a little more complicated. Sometimes there are multiple policies in place, and you don't know whether whatever you're seeing is happening because of the policy in place, or this was already happening, and suddenly you see the effect in larger amounts, and you're attributing it to a change in policy, right? So that becomes slightly more difficult, but it is still manageable. The third one is the most difficult one, where you have to prove that your cause is the main driver for your effect. There are no other variables, no other factors, no other reasons that are the main drivers or are the main causes of your effect. That is something that bothers almost every research and researcher involved in causal inference. Now, because we are getting a little more serious with causal inference, we will quickly see some of the terms that are commonly used in this field. So the first is the outcome or outcome variable. So this is the variable of interest. This is the effect that we are interested in observing. The second term is treatment. Treatment is nothing but the cause that we are interested in studying. Third terminology is covariates. So covariates are all those other factors that can potentially affect outcome. For example, let's say that I come up with a program for training teachers so that they can help primary kids learn languages better. If the languages of the students improve, I feel that they are going to do better in other subjects as well, because other subjects also make use of language. So I design an intervention program for teachers where I train them in teaching languages better to primary students. This is my treatment, right? The outcome here is I'm interested in looking at the language scores of students of these particular teachers that I'm training. Some of the covariates that I can think of are the type of school that the teacher belongs to, the class size, right? It can also be the teacher's experience and so on. Now we define what causal effect is. We know that there are three properties to establish causal effect, right? We know some of the terminologies that are involved in causal inference. Now we would like to know how we define causal effect. So causal effect of the treatment on the outcome, that is the causal effect of the cause on the effect, is defined as the difference between its two potential outcomes. So two potential outcomes. Now potential outcomes is something we have not encountered before in this talk today, right? So how we describe potential outcomes is that, let's say I have a headache right now, okay? And there is a tablet available to me. There are two potential outcomes now. A, I take the tablet and then I measure my level of headache 1 hour later. The second potential outcome is that I do not take the tablet and I measure the level of my headache 1 hour later. These are the two potential outcomes. Now in reality, one of them is going to happen. But in the world of possibilities, there are two outcomes, right? And the way we define causal effect is that it is the difference between these two potential outcomes. It is the causal effect is the difference between me taking the tablet and measuring my headache 1 hour later and me not taking the tablet and measuring my headache 1 hour later. It's confusing, right? Because we only observe one world where either I have taken the tablet or not. But here I am telling you that the causal effect is defined on potential outcomes and not before and after. It is not my headache level before I took the tablet and headache level after, which is what is popularly peddled to you all, right? That is the causal effect you are aware of. But that is not how we define causal effect in causal inference world. As you can see, this causes a lot of issues. Causal effect, right? When you define things differently, it is going to cause different issues. So now we have potential outcomes, which represents the outcome that would be observed hypothetically if the person is both treated and untreated at the same time. Only one outcome is observed and the other is counterfactual because that has never happened. We are assuming that if this happens, then what is the causal effect? So the fundamental problem in causal inference is that we cannot observe both potential outcomes for the same person or unit at the same time. So then the question naturally is that how do we establish causal inference, right? So what we do is that we try to estimate causal effect by making use of experiment. What we will do is we will try to find someone who's exactly like me. One of us will take the tablet and one of us won't. That will help us establish the causal effect between the two states. Seems easy, right? But it is easier said than done. Okay. Now that we said we can make use of experiments to help us estimate causal effects, we now try to understand the different types of experiments that we can make use of. The first one is an observational study. Now, because we are all in the same talk, let's say all of us are having headache, right? Causal inference is giving us headaches. So what I do is that in an observational study, I'm just going to observe how many of you are going to take the medication and what your pain levels are after 1 hour, and how many of you have not taken the pain medication without really influencing any of you, and then see what your pain levels are. Now, there are a lot of issues you can start thinking of that comes with this sort of a study. The second one is a quasi-experimental one, where I say that, because you have access to medication here, you're all taking the tablet. What I then do is go to maybe a nearby village where people don't have access to medication as much, and I induce headache to them of the similar kind that you have, and then I try to see how their pain levels are 1 hour after the onset of the headache to see how things are. Now again, you can start thinking of issues that can crop up with this kind of experimental study. The third kind is the randomized experimental design. This is considered as the gold standard of experiments in causal inference. Here what I do is I randomly assign the tablet to a few of you and placebo to a few of you. And then I measure, and then I see what the differences are between these two groups. And now I make a lot of assumptions here, that you're all, like comparable, and when I make these random assignments, the two groups are comparable so that I can draw causal inference. So let's look at these different kinds of experiments a little deeper. So as I said, in observational studies, we studied the units or subjects or people in their natural setting without manipulation of treatment variable. I have no control over the treatment variable. So there are many different kinds of experiments that you can think of. Cross-sectional is that when I do one study at a given time point. Longitudinal is when I repeat the same sort of study over time and see how things work. There are pros and cons of this study. Some of the advantages are that this sort of study is very practical for studying large populations. In large populations, I really cannot do a randomized study, right? And it can also help me identify long-term effects and trends. The disadvantage, however, is that I cannot establish causal inference properly, because you can think of all the issues that we are going to have with observational studies. And it is susceptible to confounding variables and selection biases. Okay, we are again encountering terminology that we have not discussed so far, but we'll see them later. Then we move on to quasi-experimental design, which is a step better than our observational study, right? Here, again, we can manipulate the treatment, right? But it lacks randomization. There is a group that is taking tablets. There is a group that's not taking the tablet. And I'm seeing that, there are differences in the group, but I'm not able to assign tablets randomly to people. This is quite popular in real life research examples, and especially in social sciences. And some of the methods are difference in differences, regression discontinuity, and so on. So the advantages of this study is that it is more practical in social settings and can be used when randomization is not possible. The disadvantages, however, are that this still has some internal validity issues. Internal validity is again something that we have not discussed, but we'll quickly see what those are. And also this design is more susceptible to confounding variables. Now, the third kind, which I said was the gold standard of experimental design, the randomized experimental design. Here we randomly assign units to either treatment or control group. And any differences in the outcome that we are observing is attributed to the treatment. So this has high internal validity. It seems like a nice thing, right? It's in the pros. And causal inference is quite straightforward from a randomized experimental design. However, there are disadvantages. First, there are ethical and practical limitations. You cannot use randomized control designs in all scenarios. And this can also be quite expensive and time consuming. And also that, it is sometimes, even if it is ethical and you're willing to spend all your resources on it, your participants might not behave in the way you want, because it's really difficult to randomly assign treatment to participants. Now we come to threats to validity. This is something we talked about in all three designs, right? We said that observational studies and quasi-experimental studies had lower internal validity or had a lot of threats to validity, whereas randomized control trial did not. So what do we mean by validity? Validity of a study is nothing but the trustworthiness or the accuracy of the results, right? It is also about how much we can generalize the results to the population and how much we can make it applicable. Now, the threats to validity are nothing but threats to these trustworthiness, reliability, and so on. So there are two kinds. One is the internal validity and the other is the external validity. Internal validity refers to the trustworthiness of the study at hand, right? Was the design suitable for causal inference? Let's say, are the methods that are used to study that particular phenomena, is that sound? And are the statistical tools that we are using to draw inferences, is that sound? All these things form internal validity. External validity is when we think about generalizing the results from a particular study to a larger population. Maybe I conducted an experiment on a group of college students. Can I take the study and generalize it to all the Indians in our country or to all the people of this world, right? That is when we talk about external validity. So statistical methods that we use or the models that we use form part of both internal as well as external validity. It is the cornerstone of internal validity, but if your statistical models are faulty, sometimes you cannot even go for external validity, right? But we are not going to focus, I mean, in this talk, I'm not going to focus on the statistical validity. We are going to look at the research design. So we will see what some of these threats to internal validity are. The first is the confounding variables. What I mean by this is that these are the variables that affect the treatment, that affect the outcome variable other than treatment. So we have treatment variable, which we claim is the main driver of the effect, right? Treatment is our cause. We are saying it is the main driver of the effect. But then there exist these variables who are affecting our effect or outcome, and we would like to basically minimize those in our study, because if those are interacting and causing our effect, then we cannot disentangle our treatment from whatever is happening. We cannot establish a good causal inference. The second one is selection bias. Selection bias is nothing but the bias introduced by the selection process of participants or subjects, right? So in the example where I said that all of you will take medication for headache, and then we can go to a nearby village and we will see how the pain levels are for the headache when they do not receive any medication, we can see that there are intrinsic differences in the two groups that I'm studying, right? Maybe because you have had better access to healthcare, your health as such might be in a better condition compared to the group that I'm studying in the village. Or it could be vice versa, because you're inhaling all the smoke in the city and the pollution, right? But whatever, but there are biases, and these are what constitutes our selection bias. Then we have history effects, which is the effect that occurs during the study that could affect the outcomes that were beyond the scope or reach of your study. So for example, let's say I was doing an educational intervention at the beginning of 2020, right? Everything was going smoothly, and then suddenly everything went online. Now things are out of my control, and things have suddenly changed. So any effect I'm going to see now has been confounded by changes that has happened. This is also history effect that has happened, and also is one of our confounding variables. So now I cannot really say that any change that I'm seeing, whether positive or negative, in the students' test scores are purely attributable to the intervention that I was doing, right? Then we have the maturation effect. So this is the effect where we naturally see changes in participants over time that could influence results. So again, some of these things are that as the course or the class progresses, it is a general phenomena that the students tend to do better. So if I take a baseline assessment and then I do an endline assessment on the same set of students, I will obviously see better results. That's because once, well, the whole point of the course is that, you know, they should have learned something, but even if I'm not doing any intervention, I will still see that students are performing in general better because they have had more time with things, they have learned more stuff and are able to answer. So these are maturation effects. Then we have the test taking effects. So this is the effect that you would observe when you have already exposed your participants to a set of test or measurement. Now let's say I was measuring the strength of people, right? And I ask them to do a particular exercise. I do that at the beginning of my study, and then I put them on a higher protein diet and ask them to do a bunch of exercises, and then again, I see the strength. But now, I'm also having some testing effects because they have already been exposed to the kind of test I do. So they have an idea of how to perform, and generally we see that once you have been exposed to any test or any measurement, you're probably going to do it better the second time. Right? So we have the testing effects. Then we have instrumentation. Again, it is related to the testing effect, where if there are changes in the instruments that you have used, any effect that you're seeing is probably because of the difference in the instruments that you used. Whether it is the test, I could have used a harder test at the beginning of my assessment, and at the end of the course, I might have used a simpler test, right, or easier test. Then any that I'm going to see is going to be attributable to the instruments that I'm using. And then finally, I have attrition, which also is about, you know, loss of participants or units during the study, which could affect the outcome. So there are panel studies that are generally done in economics, where they try to see the incomes of people and how their other, you know, like labor market participation changes and whatnot. So generally, it is seen that people who are experiencing bouts of unemployment tend to drop out of the study. They are not interested in your study. They have other troubles in their life, and they don't want to be a part of the study. But if you do not account for attrition effects, and if you just look at the median income, maybe 5 years down the line after you have done your studies, and you're claiming that, you know, the median income has grown by so and so percentage, you also have to keep in mind that at the beginning of your study, you had a lot more people, especially people in the bottom part of your income group, who were part of your study, who no longer are part of your study. So that is also changing the effect that you're seeing. Okay. Now we talk about, so these were some of the threats to internal validity. I have not covered all of those, and I've only stuck to the ones that are popularly seen in research designs that you will come across. Now we will talk about some of the threats to external validity. The first one is population validity. Here we talk about the extent to which the findings can be generalized to other populations. This is very difficult. We are all very different people, and then expecting that our research study is easily generalizable to different populations, that's not easy. However, it is one of the requirements of external validity for our study, right? The second one is ecological validity. Here, again, it is about generalizing our study to different contexts and to different settings. Again, it's not easy because an educational intervention that might work in, say, Germany might not work in India. But there is nothing wrong with the intervention in itself, right? Sometimes you have to take the study in its context and you cannot generalize it. While that is a limitation, but that should not really hamper it from, you know, being used in its context. The third is temporal validity. Here we talk about the extent to which we can generalize our study to different time points. Now, something that worked in the 90s might not work today in our own country, let alone across different countries, right? So, of course, there are issues in satisfying some of these criteria of external validity. Then we have the interaction effect, which talks about the interaction between treatment and particular attributes or characteristics of the subjects or the participants, right? In our example of you all using tablets for headache versus us going and studying people in a nearby village who are having headache, there we see that there is interaction effect between the treatment variable and characteristics of people. So ideally, we would not want to have that because that is a big threat to our external validity. Then we have reactive effects. Now, this is a very interesting phenomenon that is observed, that as soon as people are told that they are being observed or an intervention is in place, human behavior and human nature will tend to change. They will change in ways that are beyond our control, and there is no way I can possibly factor and measure each and every changes that we are observing in their behavior, in their nature, right? So this reactive effect, what happens here is that this makes our claims only applicable to the experimental setup. If you do it in a wide population without telling people you are being observed, then you might not really see the effect that you otherwise saw in the study. This typically happens in a lot of educational setting where, in the teacher training example that I was working with, as soon as the teachers are told that, this is a program that you have to undergo, we are going to test your students, they're probably going to be more diligent in their teaching. There are going to be so many changes in the way they teach, in the way they handle their class, that it cannot just be attributed to the intervention I have designed, right? And it could be that if I take away all the pressure and just introduce my intervention as is across the entire country, I might not see the effect just because people were reacting differently to the experimental setup. Now this brings us to a real case study. So a teacher training intervention was done in 2017 and 2018 to teachers of certain schools in a particular state in our country, right? So the objective of this evaluation was, we wanted to ascertain how effective was the training program in improving educational outcomes of primary students in Hindi, English, and math. So teachers were trained, and then we were interested in seeing how that translated to the students' performance in Hindi, English, and math in a particular state in our country. So here the treatment is teachers' training. My outcome variable is test scores in Hindi, English, and math. So now again, ideally we would like to test all the students from grades 1 through 5, right? But there are so many challenges in assessing students for standardized tests when they are in grades 1 and 2. So we start with grade 3, which is the earliest grade that you can basically do all sorts of assessments with. Then because there are a lot of resource restriction, we decided to go for class 3 and class 5, right? Now, you can see in this figure here that in each of the panels, you have two different years of test scores, right? One is in round 1, which was done in 2016, 2017, that is before the intervention started, and then round 2, which was conducted in 2018 and 2019, which is after the intervention was done. Okay. So right off the bat, what kind of experimental design is this? Is this a randomized experiment? No, this is not a randomized experiment, right? Is it a quasi-experimental design? Yes? Do you have a control group here? No, we don't have a control group. So we don't really have control over our treatment. Treatment is there for everyone, right? I'm not able to say that there is one group with treatment and one group without. But it is still slightly better than our observational study because we have 2 rounds of assessment for the same set of teachers, for the same class. Okay, so what are some of the issues that you can think of? Because we have already talked about threats to validity. What are some of the issues that you can think of with this sort of a design? Yes. No. The number of students were definitely not same. Okay. One factor is that the number of students changed from round 1 to round 2, right? Different, because it's different years, right? So you have a new cohort, different cohorts. So of course we have selection bias. Okay, so we have selection bias, we have different number of students. We might have maturation effect, right? So people who are in class 5 here in 2018-19 were in class 3 in 2016-17. There is some maturation effect, there is some test taking effect and whatnot. Okay, so there are a lot of issues with this design, right? So a side note is that why we don't have a control group here is that nobody wants to spend money on assessing students who have not undergone any training. Right? The government sees that as a waste of money they have to do. So in social settings or in educational research, whenever you're working with causal inference, it gets very difficult because of a lot of resource restriction. So you have to come up with better quasi-experimental designs. However, in this particular study, they did not really make use of good designs, but that is actually the nature of causal inference that is actually happening around us. Right? Okay. So based on the diagram here, what would you say? Would you say that the intervention was effective? Mm-hmm. Right. So we are seeing that in 2018-19, the curve is shifting more towards the right. We are having more students in the upper percentiles or upper percentages, right? So that sort of tells you that maybe the intervention was effective, but you cannot definitely make causal claims. You cannot say that the intervention is leading to the effect that you're seeing. Also, other history effects, right? Since 2017 or 18, there has been a greater push for use of technology in classrooms. So a lot of rural classrooms now are equipped with smart technology and they can make use of those. So with pushing of technology in classrooms, what we have found out is that students are having more exposure to English language, because a lot of videos or a lot of resources are created in English, and most of the times they are translated, if at all, in the regional languages. So you see that greater gains are seen for English language, right? And that can potentially be attributed towards this whole shift of involving more technology. So when you are doing causal research in a particular field, you also need to know a lot about what is happening around you, right? That is the only way to sort of account for a lot of confounding variables. So to summarize, there were a lot of issues with the internal and external validity of this particular study. So confounding variables, right? There were many confounding variables that were not accounted for. There was selection bias because there were two different cohorts that were being measured. There were history effects, there were testing effects. And then we know that there is interactive effect when students, when teachers are put under this whole, sorry, there is reactive effect because the teachers were, teachers who underwent the training were told that, this will be evaluated and the students are going to be tested. And then we also suspect there to be some interactive effects because the way the teachers were sampled for the training was such that their principals basically had to sign up for the program. Now, principals who are signing up for such programs are probably going to be more involved in bringing changes in school and implementing certain policies, right? So there are characteristics of the participants, and that can potentially be working with the treatment that we had in mind. Okay. So there were so many different issues that we saw with the causal claim, and I have not even touched the statistical analysis that was actually done to claim that the teacher training intervention was effective. So this particular training was uh, deemed to be a success, and they made use of this intervention for all the government and government-aided schools in that particular state. Now, this is a causal claim, right? And we all now know that there are a lot of issues with the study that happened. And crores of money is spent on such programs. So causal inference is not just about whether, like eating chocolate is going to boost your IQ or anything, but these are going to have a lot of ramifications for our education policies, for our economic policies, and such. So another case study. This is a news from yesterday or 2 days ago, where there is this claim that BPA, we talk about BPA-free plastic, right? If you're drinking from your plastic bottles, it has to be BPA-free. A lot of food containers and whatnot, they say that we use BPA-free plastic. So this study tried to see whether what was the causal effect of BPA on diabetes. So what they did here was that they took 40 participants, 40, right? And this particular study is being sensationalized by a lot of media houses, and you can just Google this and you'll find a bunch of articles on it, right? So there are 40 people who were there in the study. And these people were selected, it seems like they were all college-going students, right? We had 22 females and 18 males, and the participants were then randomly assigned in a double-blinded fashion. So what kind of experiment was this? Yeah, this was a random experimental design. So we have slightly more faith in the internal validity of this particular study, right? And then what happened was that 2 sets of measurements were obtained from these people. One at the baseline and one after 4 days of a particular treatment, right? The treatment was such that US FDA claims that, up to 50 micrograms per kg of the body weight, if you consume BPA, it's fine. What they did was that they randomly assigned this particular treatment, BPA, to few people and placebo to few others, and then basically saw what the effect was on 4 different things: body weight, fasting blood glucose, urine, and insulin sensitivity. They did this at the baseline, and then they were put on like an energy balanced diet, and then after 4 days, they tried to look at the measurements again. And then they found out that they did not have any significant differences in body weight or fasting blood glucose between the 2 groups, the one that was receiving BPA and the one that was not. And they saw that there were differences in the urine levels and insulin sensitivity between the 2 groups. They have not mentioned, at least in the abstract that was available, they have not mentioned what the differences were. But if you see, the insulin sensitivity that they claim has significantly decreased, which is a bad thing, because if your insulin sensitivity decreases, that means you're more likely to get diabetes. So insulin sensitivity decreased in the group that was getting the BPA dosage, and it remained stable in the placebo. But you can see what the differences are. While they have probably had a lot of internal validity in all the different things that we discussed so far, this still tells you that, should we really buy into the hype? I'm not asking you to drink from any plastic bottle, okay? Just because I'm saying that there are issues with the study here. You should be still careful and maybe heed to it. But the thing is it worth the hype? Can we generalize the study? First of all, is the study generalizable? We have 40 people, 40 white people, right? Can we generalize the study? No. There are so many issues. Okay. So some of the factors we have to consider apart from these different threats that we have already talked about is the sample size. Right? This was also pointed out that in the teacher training intervention, the sample size of the students from one cohort to another might have been different. Yes. Here, in the second study, we saw that only 40 people were randomly assigned to treatment and placebo. Right? So the sample size, we need to ask ourselves whether the sample size used in this study is sufficient to support causal claim. 40 seems too low, right? Then we have to discuss about sampling strategy. Was the sample drawn from a probability sampling method, or was it non-probability? So non-probability is when we do, convenient sampling. I basically administer a survey of all the people who are willing to answer my survey and then draw conclusions based from it. It's a very convenient sample that adversely restricts the generalizability of my study. Then representativeness. This is also somehow connected to sampling strategy, right? So how does the sample accurately represent the population to which the causal inference is being generalized? And the last is, do the research design and statistical model appropriately support causal inference? In this talk, we have focused on the research design, right? For a robust causal inference, we need to have a reliable research design and a cutting-edge, robust statistical model. Only then can we make causal inference. So as you can see, that causal inference is very challenging. It's easy for us to take any research and dissect it. No research, no causal research is going to fulfill all the criteria we listed, and I listed only a couple of those. Right? There are a whole lot of things that a research has to satisfy in order for it to be like everywhere and applicable everywhere, right? So causal inference is very challenging. The second thing is that the design of an experiment is very crucial in causal research. I would say that the design of experiment is crucial in any setting, because what you have messed up with your research design cannot be undone by any statistical model that you would like to use. So the focus of this talk is on paying attention to the research design. A lot of times, statisticians or data scientists or people who are interested in quantitative analysis are involved in the later stages of the study when all the data has been collected and you are basically given the data to come up with the values that they can use. That is a little too late in the process for a statistician to be involved. Ideally, it should be right at the beginning so that you can guide them through proper research design. And ultimately, I would say that, as someone who works in causal inference, I would say that we make use of interesting and novel regression models to make causal claims, and it's fun. It's challenging, but it's fun. And I would urge all of you to maybe take some interest in causal inference moving forward. All right. With that, I end my talk, and I open the floor for questions. Thank you. Thank you for your attention.
Are there any questions?
Okay. So if you want to assess, or do you want to like analyze those for yourself? Okay. So to believe in it or not, basically you have to see some of the factors that I mentioned at the end. You have to basically see whether they satisfy those, and maybe not pay a lot of attention to external validity at that stage, but see whether some of the internal validity criteria that we discussed, are they fulfilling those? Those can be like the first steps to see whether the study is something you should invest your time in. Because a lot of times we hear about, doing exercise in the morning is best for weight loss or for health, or intermittent fasting, good for you, bad for you, coffee, good for you, bad for you. There are so many articles about such things, right? And in fact, nutrition science is one of the low-hanging fruits of causal inference bashing, because they make a lot of causal claims without really employing any good statistical designs or methods. So yeah, I would say that, maybe first try to assess whether they satisfy, first of all, the three criterias of causal inference. That is, are they related? Are the cause and effect related? Is there a temporal precedence? And is the cause the main driver? After that, I would say that maybe look at some of the threats to internal validity and things like sample size, sampling strategy, representativeness, and so on.
Are there any more questions? Okay. So thank you, ma'am, for the informative
Thank you.
talk.